Hello all, thanks for joining before time. So sorry, on time. We'll wait for say, let's say 5-10 minutes and to have a couple more people join the meeting and then we can start. Okay, so hello all. Welcome to this live session. So we are already 5 weeks, and probably the content for sixth and seventh week is already up there. We'll do the things that we usually do. So first, following up by my introduction, I'm a PhD scholar at IIT GN, IIT Gandhinagar, in the discipline of biological sciences and engineering. I'm currently in my third year. I work in quantitative ultrasound field for tissue characterization. So my basic goal is to differentiate types of tissues, let's say a normal tissue with respect to a cancerous tissue. So I'm trying to delineate them via their boundaries. So if a particular surgeon, if it can help a surgeon do early prognosis, and he or she can is like avoid unnecessary biopsies that are being done nowadays, even for say borderline cases like basic lesions or cases that are like can be very benign, can be on the verge of being malignant. So that's my work, and I'm a PMRF fellow. So part of PMRF duty tells us that okay, you need to go somewhere, or else you need to TA for any other different institute apart from your own institute. So I'm TAing for this NPTEL course, that is data analytics with Python, under the guidance of Professor A. Ramesh. So till now we have seen a couple of things, and this is following up by the last week's content. That is nothing but the fourth week. Okay. So what did we see that, okay, why, what, and how, why Python is needed, or sorry, why data analytics is needed, what's the perfect right methodology to do it, how to correctly use it and interpret it. So our objective was to understand the data, and that's from where actually we started, the types and the differences in between the analytics and analysis. And then we came upon the point that, okay, why Python is needed there. So we saw that the confidence interval estimation, and that is from where everything started, that we need to know that which particular things will lie in between which intervals. So let's say for stats, we usually take like 90%, 95%, 99% confidence intervals. We looked upon, okay, well, my cursor is not on. We looked upon this particular distribution, Z and T distribution, and now we know that why we are using this distributions, like when to use those, when the standard deviation is known, not known, when the sample size is like less than 30, greater than 30, what is termed as sample estimates, what is termed as population estimates. After knowing all of those, we can just go and formulate a confidence interval and then create a confidence interval for a particular population. Okay, so then we saw that, okay, what was a point estimator, a sample estimator, an estimator of the same, and the sample and population statistics. There was also something called as unbiasedness and biasness, how to check for those, and how confidence interval lies in if it's for a particular range. Okay, so this was how the entire process of sampling and estimation was like. Now, after that comes a process of, okay, this was all about T distribution and test, and I guess then we solved certain things. Then we had a concept of hypothesis, that, okay, I need to solve for something and I need to know that how should I proceed? So for that, I'll take two hypotheses. One would be my null hypothesis, another would be an alternative hypothesis. What I actually want to do would be my alternative hypothesis, but there's only one condition, that alternative hypothesis cannot have an equality in it. So let's say if something is asked to be that, okay, I will eat ice cream today. So, or from starting today, I'll start eating ice cream. So that is like something like, okay, today and more than today. So, or following consecutive days. So that's like greater than equal to. So at least something. But in alternative hypothesis, I can't have an equality. So alternative hypothesis would be, I will start eating ice cream. So it's like, or from today. So that would be only greater than from this particular day. Whereas null will consider an hypothesis that is very less than and will also have equality in it. So how do they are they represented by, so H naught and HA are the typical symbols for them. And there are these two errors that we usually have. So type 1 and type 2 error. One is your acceptance error, that is type 1 error. When you say that, okay, sorry, incorrect acceptance. Yes. So there is like, okay, was it incorrect acceptance? No. Incorrect rejection. Yes. So you say that your null hypothesis is true, but again you rejected it. So that's an incorrect rejection. You could have accepted it. So that's a type 1 error. And that usually you take within a certain significant level. Next in the type of error is type 2. So well, type 1 error is represented by alpha and type 2 by beta, whereas type 2 error is, okay, it's false and though you're accepting it. So that's an incorrect acceptance. So false acceptance. These are the two type of errors that you usually encounter when you're doing with handling with stats. So that's all was to help you build up on your basics. Now I saw that, okay, the last week's session were more heavy on formulas. So hence I thought, okay, we'll directly go upon the actual lecture slides and we'll just hover them up and see the formulas too, because we have seen that many of you are not able to solve the assignment questions and you are getting somewhere wrong, or probably you don't know how to exactly read the tables, or can be you don't know when to apply a particular distribution for. So hence we'll just go directly to the entire material and just hover through there. It won't take much of the time, let's say 30-45 minutes-ish, and then we can go towards the assignment of last year that will help you solve the assignment that is incoming. Okay. So next was hypothesis testing, where you will assume, okay, the population variances were not known to you and were assumed to be unequal. So everything now is like normally distributed. So there were this all categories that you have. So when it's known, when it's not known, when they are equal, when they are unequal. We have already solved for the known ones and equal ones. Now we are upon a stage where it's unknown and unequal. So for the same, you'll have your variance. So now it can be a pooled one. So we are assuming that the variances are unknown. So you need to account for two different variances or sample variances for two different populations. Okay. So similarly, you'll compute the variance of it. Now, why n minus 1 is here, if anyone can say that thing? Well, let's be interactive so that you'll go through the session. So what does n stands here and why is here n minus 1? Oh, sorry. I just realized that I have not given you all the access to turn on your mics. Well, okay. You can unmute yourself and let me know that, okay, what is n1 and what is n1 minus 1? Why can't it be n there?
Ma'am, n minus 1 means the degree of freedom.
Sorry?
N minus 1 means degree of freedom. The n is the sample size.
Yes. So why do we always take n minus 1?
Mm,
So what
Don't
the
know.
student, sorry?
Don't know, ma'am.
Oh, okay. So, well, what you
Because
hinted at,
the parameter is unknown, that's
huh,
we do n minus 1.
well, you are on the right track, but why do we take degree of freedom? And the concept of degree of freedom is like if you try and change the last sample of your population, the mean of the population won't change. That's why whenever you are dealing with samples, you don't want that the mean of the particular sample population should not change. So hence you have a concept of degree of freedom. So you fix your mean and then you try and play with your entire sample population, as in how it gives you more realistic assumptions towards your entire population. That's why people consider degree of freedom there. Okay. So then we saw, I guess the last slide won't come here. So we'll have to reload this. So then, okay, this is a simple thing again, the how to compute the test statistic for it. So that's difference in your sample means the difference that you take in account and divided by the standard deviation. So here they solved an example for the same. How this example computed. So you compute the sample means over here. Probably this x bar might have been given. This would be your sample standard deviation. And then you assume a particular hypothesis. Now over here, if you also see, null hypothesis accounts for the equality, whereas an alternative hypothesis does not. And you compute the t statistic. The difference was 0 there, so hence they don't have anything. They computed the degree of freedoms accordingly. So that's nothing but the population size minus 1. It can also be different for the numerator as well as the denominator. And then you you see that where your particular T, so if you know how to read a T table, it's always like, okay, you have been given, you need to find the values across that particular index for the degree of freedom, then you get the probability. So here the probability that you have been getting, then again you see that, okay, is it after or below my critical point? If it's yes, then you reject the probability. If it's not, sorry, the null hypothesis, if it's not, then you accept it. So here it was, so hence the evidence was that, okay, there was a difference in means. So you just, numbers are given to you. The final thing is just to read this particular table and to know that, okay, where you want to take that particular value from. Okay. So here the evidence and how to frame your, so okay, you say that reject the null hypothesis. You can't say that the null hypothesis is wrong. It's like, okay, you are just taking a hypothesis to begin the statement with. So hence you could always write that, okay, they were different from them. So it's not that you can't statistically, it's like writing that, okay, this was wrong, or considering that the mean of the population of these two, say sample 1 and sample 2 populations are not equal. So we can't say those things in stats. That is something like statistically wrong. What you say that, okay, it is different from, because the actual stats, the values for the population, what is true is not given to you. You are making assumptions based on a smaller set of population. Okay. So similar things you can also do on Python. So if you do and you find for the indexes for them. So here I've done something similar. So when the population variances are not equal, you just load your NumPy. Okay, wait. We'll restart it. We'll clear all the outputs. Well, this is a Visual Studio Code where we are doing all of these things in. Okay. So we'll import the libraries like this, import numpy as np, and so similar the way how it was over here. And when they are not equal, so T statistic, and what does PPF stands for? It's nothing but probability mass function or probability per value function. So here you see it's like the value that you against you want to compute it and your degree of freedom, that is like will help you give this t statistic for that particular value. Now okay, that was something random, probably that what I did there. Now over here, if you have something like, okay, t test across this particular index, and then you say that, okay, the equal variances condition is false here, so variances are not equal. So what you get over here is something like, okay, your p value here, it's like 0.01. And what did we assume at the beginning? That it was like, say, 95% significance. So, well, again, it is less than 0.05. So we can say that, okay, we can reject the null hypothesis and we can accept what is true with my alternative hypothesis. So what the solution or the conclusion that we came upon, that was, okay, it is different. So if you want to, you can calculate it also and you can see it if you know and how to read the particular table. If you don't know, you can also compute it using this particular way. But it's always good practice if you know how to read these tables. Well, it's not that hard. If you just see for a couple of times, you would be easy to, it's like, it would be easy to understand those tables. So it's simply indexing that you need to follow and understand that what particular, say if it's like 95% or half of it, so alpha or alpha by 2. So you need to understand those things only. Or else Python gives you flexibility, it will compute it for you and you don't need to look for anything apart from that. Okay. Now let's say if, okay, someone's joining. Okay. So this is how that particular sample was. And now if something is dependent, so you have two samples that are dependent. They can be paired samples, match samples. There can be two measurements, can be before or after. So what you do is like, so how come this thing before and after thing comes when? So it comes like, let's say I did some experiment. My experiment is something based on the forenoon and afternoon period. Sorry. Yeah, yes. So it depends on the afternoon and forenoon period. So I'll say that let's say my tissue is behaving something different, or the cells in my tissues are behaving somewhere different, and their mechanical properties that I'm getting are different when I'm getting it exposed to the sun after a certain period of time or not. So that varies within the time period or the temperature that is varying in between forenoon and afternoon. So that is something like before this thing, after this thing. But what is that particular thing? That's nothing but my cells that I'm focusing on. So there's only a single variable there. So I can pair them both. I can match the samples. I can consider that, okay, these samples are dependent on a particular variable, hence I can take them. For example, here we just took the previous example. So that was like metro and rural. So if the population there is related in certain ways, can be a particular variable that you might want to choose in. So here, if you see the function changed, it's like rel. So that is nothing but it's for dependent samples. It stands for relative. Okay. So if you see here, the p-value came to be around 0.03. So, well, of course, we can say that, okay, we reject the null hypothesis and we accept that these particular mean population differences are different for these two populations. Now, how do you compute it when you need to do it? So that can be, you take the difference, you have the initial difference, a hypothesized mean difference, and similar. So you have your standard error at the bottom. How do you compute the differences of the mean? You take individual sample difference and then you take the mean of it. Okay. I hope that's pretty straightforward. And if any one of you faces doubts in it, you can simply unmute yourself or can raise your hands and can let me know. Okay. Next, you have like this sample. So we as like in previous sessions, we saw via the curves that okay, how a particular test can be lower test, upper test, or can be two-tailed test. So if it's greater than something, if it's lesser than, you see which particular side the your hypothesis lie along to. So if it's your alternative hypothesis is less than 0, so you say, okay, it's a lower test. You follow everything according to the alternative hypothesis. Now, if it's greater than 0, it's your upper tail test. If it's equal to or not equal to, it's both sided. So that's your two-tailed test. Okay. So same thing that is given over here. Okay. Now, so this was the thing that I was saying. So your for T table, what you need to see is first is your degree of freedom, next is your confidence interval. So across to which particular confidence value you are looking your probability ranges across. Okay, there's again one more example. Yeah, I guess it's the same thing. So you compute the relative difference in between these two particular population cases. Now there is a thing called as population proportion. When do you want to consider population proportion? When your samples or your variables are not continuous anymore. So they become categorical. So you need to consider what's the count of them. Okay. So then people assume that the interval estimate and then you do estimates across those particular tests. So everything would be now in the terms of P and Q. So P is like Q is nothing but 1 minus P. So probability of success and probability of failure. You take expectation of the same, you also take the standard deviation of the same, but everything that you now accounted for just P can be for two variables in the P and Q. So two samples from the same population. And this can only be done when your value is like the sample size is sufficiently high enough for this population. Now, high enough, you might also say that, okay, it might tend to normal distribution. Well, it's correct. It will tend to normal distribution and hence you are trying to use a Z or a T distribution here, okay, or T test. So you say that, okay, it's greater than 5 or NQ is also greater than 5. So you need to see that these conditions allow, or else your test statistic won't give a reliable result. To compute here, the values you can compute. But for statistics, we need certain number of elements to say that it is true for the entire population if you count for this many number of population. Okay. So same thing here, the example is also given for the same. So if it's left-sided, right-sided, and two-tailed, the hypothesis follows the same pooled estimate. So, okay, you take the weights of them and then divide it by the entire sample size of the population. So the reason why I'm going through all of these slides is because you to see the formulas of the same so that while solving examples, you should know that, okay, which particular slide should I take this particular thing from? Well, of course, last year assignment questions are pretty easy to take it on and you don't need to memorize all of these formulas. But memorizing these formulas is nothing. It's like all of the formulas follow same trend. If you look, it's always the difference of the mean minus the difference of the hypothesized the mean divided by your standard error. If it's not the error, you compute for the variance and you take square root of it. So it's always the same. If you feel, okay, there are a lot of formulas that I need to remember, you don't need to remember all of the formulas. Okay, similarly for this test statistic also. So what here they did was they computed this particular sample code for two test statistics. So two sample proportion. So it's nothing but they have just directly written these formulas if you see here. So you take the difference in between these two means. Sorry. So here they have taken a pooled one. So here, if you go, oh, okay. So here you take the sample, you know the sample size of it, you know the first population proportion, second of one divided by the entire sample size. So it's just exactly writing the entire thing over here in basic words. So how do you write the equation? Same words. It's no one does not need to know Python in order to write the formulas. It just directly you write. But well, of course, in Python, there's like there are no such things like, okay, if I want to do x square, you can't do something like this. You always need to do something like this. So certain things in Python are different, but well, of course, those aren't that different. For square, division, everything all remains the same. Other formulas are not so different. Okay, where we were. Okay, then we just found the population proportion of it. So this is PQ divided by this particular thing. So this is a denominator that we're trying to figure out here. And this is S uses or square root of it. Finally, Z is nothing but difference by the sample statistic. So here we considered that, okay, the value was 0. The sample difference was 0. Now, how do you compute the probability of it? The probability would depend on the CDF. Well, of course, the at least value is like value till now is like if it's less than or greater than, or else it would be 1 minus of it. So that is nothing but across the distribution, you're saying if it's less than that particular value or the rest of the value. So if we see another such curve here, how to understand that particular sample. Well, of course. So if you say, so for a particular value, let's say this minus T alpha, this critical value, my CDF would be till this value. So first P, when this is less than 0, will give me value still here. What will 1 minus stand for? This is nothing but probability from this particular value to the rest of it. Okay. I hope this particular lecture was easy to digest. And then next is, okay, how do we see that, how do you compare these two population variances, how to choose if it's SZ or T. So why these things are repeating? To remember you or to help you remind that when to use a particular test, and you don't always end up using T or Z, and you'll think that, okay, I wrote a formula for Z, that's what the particular person did, but I'm not getting all the variables that are required in here. How should I do? Z table won't you even have values or indexes for those numbers if you are trying for, say, a lesser number of population, a smaller sample size. So these are the things you need to know, and hence the lecturer is trying to repeat these things after a certain point again and again. Well, I'm not saying that all of the things will be repeated, but this is just done so that you understand why we are doing these things. Okay, so next is you see the population for two variances. So this is the thing that we solved. Okay, so then comes a thing that, okay, you compare the variances of the two population. Okay, so you check if the population variances are same or not. So for the same, we have another test that is called as F-test statistic, which helps you know that, okay, if the variances, so before doing any other test such as the t-test, or there would be another test that will be looking further. So before doing those, you need to account for the variances of your population, if they are equal, if they are not equal, if they are different, something like those. So you have something called as variances of it. So where first one follows its own degree of freedom, another one follows its own degree of freedom. So for the numerator, we need to account separately as well as for the denominator. Okay, so this is how you just compute it. So if your sample size is same, it's basically what is nothing but you get cancelled out. So that's essentially your standard deviation or your variance. But if it's not, then you also have your standard deviation there. Okay. So here, what is, if you use, like, you might say that, okay, this is only for a single side curve. Well, it's not. It can also be for this left side also. So here we are saying that we'll reject the hypothesis if we are within this region, and will not do not reject if we are within this region. So that is statistic, and for which particular value that we are actually looking for. So here the variable or indexes that you might want to see are like n-1, n-1. So for x and y, and that's alpha by 2. Here it's like only alpha. So your confidence interval matters, very much it matters. Here it's like two-tailed one. Here it's like a single-sided one. Okay, so try and understand what's the difference in between them. So here one such example was there that, okay, they gave you sample sizes, gave you standard deviation. You just want to first formulate a hypothesis. Null would have an equality, alternate won't have. You compute the degree of freedom for the numerator and denominator, and then you compute the confidence intervals for the same. Now in this case, what happened was that you don't know what the value of this F table will give you for 0.95. So they again also showed you in the video that if it's for 0.95 and that's like for 15 and 10, you reverse those two values. So first you compute for 15 and 10, then you go and compute for 15 and 10 here, reverse them, and then take its inverse. So you'll get a value for another one. So these things are much more simplified here. If you have any doubt, you can just let us know, and you can also reach out in the discussion forum. Okay, but similar things we can also do in Python. So if you don't want to read the table, and if it's like just makes no sense, well, of course it made me no sense for me that why are you just reversing this indexes and taking its inverse? There might be some exact formulation for the same. That's why you have something like Python over here, where you do the F statistics at that particular value for the probability of failure as well as the probability of success, and you compute and see what your F statistics gives you. So those are the two values that you have with you. Now, if again you want to compute the population variances, how it would be, and the degree of freedom for the same, you'll also get the p-value for the same. So here you can see that, okay, it is well less than 0.05. So we can say the conclusion can be that it is not equal or they are different from both of them. Okay. So this is the basic idea. How do you always consider which one to take, whether it's z-test or it's t-test? So if your sample size is always lesser but you know the population standard deviation, you can go with z-test. But if it's not known and if it's also less, then you can go with the t-test. Whereas if your sample size is greater than 30, don't think of t-test, just go with z-test, because now you have a good idea and approximation of the entire population. That's why with stats we say that 30 is the magic number. People in the past, back later, they came up with this number and they saw that when the number reaches this particular value, our distribution becomes much more normal, and we are able to see that our sample population very likely represents the population distribution. So hence we rely everything with this particular number. But that might also have something from where it came upon. So we have a concept called as the sample size. So how do you compute a sample size of a certain thing? So I like some of you to say that what did we learn, what was alpha and what was beta.
Alpha is the type 1 error and beta is the type 2 error. Alpha means accepting H naught when it is true. Beta means rejecting H naught when it is false.
Very good. So we need to account for these two errors while computing our sample size, and there's also a given significant level to these. So alpha stands for a 95% significant
Hello,
population.
Andy.
Okay, please mute yourself. Thank you. So, and beta stands for 20% significance, if not can be 10, and that is something that you can change with respect to your research question. Okay. So then again, two-tailed hypothesis, it can be z alpha by 2 and not z alpha, that is for the one-tailed population, right? So there are different sample examples that are given over here. So you determine a sample size for them. So it just the values were given over here, z alpha stats were given, beta stats were given. So here, for example, they considered 95% significant, that's like you have 5%, so 0.05, and here they considered likely half of it, so that's why it's 0.1. Okay. So then simple again question, how do you compute it? So just write it exact simple code in Python and then follow it for say some another function, give it some random values and see what your sample size comes around. So beware that in this particular alpha, beta, mu1, mu2 and sigma. So mu1, mu2 and sigma are something that depends on your own population. Whereas alpha and beta are those things that depends on your own research question. Which particular level of significance or at what percentage you want in your population to be around. So those are the things that depends on you, or probably your research advisor can help you guide with these things. If you're say writing a proposal, these things called as power analysis, sample size estimation, what's your type 1 error, what's your type 2 error becomes very necessary. Or else even state agencies which are funding you, your proposal, your application won't even give you funding if you have not written anything about stats, or you have not mentioned how will you do stats, which particular measures will you take, what's your different types of errors, and what finally would your sample size, how much population do you want your study to be conducted with. So these are the things which comes pretty handy if you know these things along. Okay. So this was all about the, I guess, the second one. Next, we had something called as, so now we saw that the F test was to compute if your variances were same or not. It's like how your variances in between two populations vary. Because indeed, we are checking for two groups here, right? Now, the next thing was we checked for the t-test statistics. That was also when your population size was less than 30, and Z when it was greater than that. We saw the sample size calculation. Now, there is something called as one-way ANOVA. So it's like analysis of variance. So first we'll just see how to compute sample size when you're estimating the mu of the population. So this formula for Z remains the same. There's no difference in between it. right? So that's nothing but x bar minus mu divided by your standard error. Now, if you're estimating a population sample size, and if it's a two-tailed distribution, oh, well, sorry, you need to estimate for the error. So what error would be? Would be a difference in between the mean, the sample size, a sample mean, and your population mean. You compute it, your sample size, in this case, it's something given by z sigma divided by your error, and you can estimate your standard deviation to be 1/4 of your range. So well, there's no particular citation for this. How come it came as 1/4 of a range? I was not taught in this way. I'll confirm this and will let you know that why it's exactly 1/4 of that range. For now, you can just consider it, or if you don't want to let it be, I'll let you know in the next coming up lecture. Okay. So he, sir, gave examples for the same that, okay, wait. He gave examples. Okay, your error is 1, sigma is 4, and then you input it and see how your population sample size will come. Now, always consider these things that, okay, when to take a seal or a floor. So what do these two different things mean? When to take a lower value, or so when to approximate it towards your floor value, or when to approximate towards your ceiling value. So upper or lower values, which particular way you want to go through. So samples like you always want more of it. So you don't want that something would lack. So let's say I have my own birthday party. I want to distribute X number of chocolates, but here I don't know how many people will come and attend my. It's like I have given invitation to a couple of people, but I don't know if all of them would come and attend it or not. So I'll assume that okay, if I've invited, let's say, 25 people, I'll take chocolates for 30 people. So I'm always on the upper side so that I don't lack something. My research would not lack for a particular thing or not. So that's why when estimating sample size, will always go towards the ceiling of a particular value. So the upper estimate of the value. Hence now approximated to 44. Okay, so if you might see that, okay, if you approximate it to the third or second decimal point, it will always come up to be 43. But for sample size, you always take the ceiling of the value. Okay, similar things here also. Then it's for the population proportion, so it's pretty much similar. Same thing. So here you didn't know the standard deviation, so you estimate it across the 1/4 thing. That's just the gate. Okay. So now why ANOVA and what is ANOVA? So ANOVA stands for the analysis of variance. Now here, when you do t-test statistic, what do you do there? You compare in between two different groups. Okay. And following each particular test and a t-test statistics, there is a type 1 error associated with it, right? Now, what is the error? The error is this 1 minus alpha. When you do this test, alpha is again your type 1 error. When you do this test couple of times, the error increases by the number of times you do it. So by the number of means. So that would be 1 minus alpha raised to k. Now, if you have more than two groups, so what will you do? If you say, let's say you have A, B, and C, three different groups. You're doing test statistics in between A and B, then you're doing B and C, then you're doing A and C, something like this. N number of permutation combinations that are possible there, you're doing in between all of them. Each and every time your type 1 error will consistently increase, and you don't want to do that. So let's say even if your significance level comes to be certain value, you are rejecting it by this many times of error that was accumulated in the process, and your research could have given more significant analysis to you. So that's why there's this thing called as ANOVA, which will help you. Okay. Which will help you compare two or more than two groups. Okay. So if you have, let's say, three groups or four groups, you always do ANOVA with it. You don't do t-test statistics. So this is usually a common error. What people do is like, okay, I don't know ANOVA, I don't understand the meaning of ANOVA. What I'll do is like, I'll compare multiple groups again and again, again and again. Whereas ANOVA gives you the flexibility that it will compare all the groups for you, and the error that would be counted would only be counted for once, would not be counted for each and every time you keep on iterating the t-test statistic. Okay, it is indeed doing t-test there, but it has its own purpose, that why it's doing, because it's being made to compare multiple groups there. Okay, I guess my network's not stable. Am I audible to all of you properly?
Yes, ma'am. Yes, ma'am.
Okay, thank you. So then again, we saw that there were chi-square tests, and these were only for this population proportions. Now, if you have your z-test, the generalization of z-test for this particular kind of test, or more than 2 groups or 3 groups, is the chi-square test. You have your ANOVA for your t-test. So these are the two different generalization that you have. And if someone asks you that, okay, what can be generalization of z-test when it's for a certain population proportion, when you are this thing, when you have to compare more than 2 groups, so that's like chi-square test. For t-test, it's ANOVA. Okay. So same thing, same process follows, and you need to account for the measurements. So this is where your measurement of acceptance and sampling goes to. If you're not accounting it properly, your design of experiments will lower down. If you are doing it, the acceptance samplings becomes more and more, higher and higher. Okay. So this was another such example. So there are the 3 different terms here. So these are nothing but to account for the error, sum of squares of errors, your sample variance, and your sample bias. Okay, so what your ANOVA table gives you, it will first see the sum of square variations, it will see the degree of freedom, it will see the mean square differences, it will see the F statistic, that is how the variance in between the populations vary between group and within group. Now, what was that concept? In between the groups and in within the groups, it's like out of the group and in between two groups, like that. And for that, something called as degree of freedom there for a particular group is very responsible. So then at the last, it will tell you one p-value for comparing all of the groups and if they are significant or not. So here probably it compared, let's say, 2 groups, and that's why it's giving us one p-value, and there are only two assumptions or formulas for the same. So that was how it was. Probably here some example would be there. Yeah. So ANOVA can be one way and can be two way. When two way comes and when one way comes, it's nothing but how do you start and see your comparison within. If you're comparing just one way, compare all of the groups directly. If you want to compare in between two independent groups, and that's the way, one can be this way, one can be another way, you do a two-way ANOVA. Now this one way and two-way ANOVA are something like you can't compute it by hand, and that is why software is called as, this Python is there. You also have something called as origin where you plot, but there origin also gives you access to do statistics. There's also one more software. I don't know if I'm allowed to say it loud here, but it's a good software. It's a GraphPad Prism. So it also helps you do the statistics in a much more convenient and faster way. Well, of course, doing your stats in Python, MATLAB, Origin, GraphPad would have different values, but finally the trend would come same. Trend in the sense that your significance p-value might differ because all of the softwares would have different optimization algorithms, and for all, you can't expect your significant digits to be exactly same. But if one is giving you significant results, all of 3 should give you significant results. So if you are, let's say, following Python, be consistent with Python. If MATLAB, MATLAB. If you're doing GraphPad, be consistent with GraphPad. Do not compare one software's analysis with another software's analysis. Just compare the trends of the two, how your data is incoming there. See how your box plot fits. See how your particular values comes out to be. So those are the things to be compared with, and those are the things that researchers like me or learning researchers always or can somehow confuse with. Okay. So here, one such case is to do one-way if ANOVA. So it will also give you all test statistics value along with the p-value. Now p-value is not so less than 0.05, so we cannot reject the null hypothesis over here. Okay. So there's one command called as melt here. So what will melt do? This melt command, it will probably it will take some time here. So what this melt command will do for you, so if you see over here in the comments, it will help you unpivot a particular data frame that's like from too wide to too long, optionally leaving some identifier set. So if you want to say, let's say, if you have been given a particular spreadsheet, from that spreadsheet, if you have say certain, for here, let's say for my example, I've taken a student marks Excel sheet, okay, and now I have different subjects. I have the marks of them, but I want to make it generalized. So what will I do there? Oh, okay. So let's first load it. Okay, so that's nothing but followed by simple pandas, read CSV. We loaded the entire spreadsheet that we had. Now, if you see the spreadsheet is like having gender, date of birth, maths, physics, chemistry, all the subjects there. But I don't want it to list in that way. What I want is, I'll reset the index of my metrics. What my index variables would be my own index that's already there. My value variables would be all these particular subjects that I want, and I'll give that particular value variables a name as subject. Okay, and the name for that particular variable would be my marks. So how do you do this? So this is the way I got it. So for number of 10 number of people, the index is something like this. The subject is maths followed by their marks. So it helps you give a more generalized description. Well, now if you see, what we have done is made a new variable called as data new, and where your entire data set is being stored with. You are not at all manipulating what your data you had here. So if you do something like what we previously saw, if you're indexing, changing the index there, we had to reset our data set to its original values there. Here we don't need to, because it can take in an entire array into a new variable and can do those statistics there, because we aren't making a data set again. Instead, we are just changing how it should be represented there. Okay. Now, why it is helpful here is because, okay, so we have changed and transformed the variable. And now if you want to compare the t-test statistics there, or if you want to compare these particular values in between certain distributions there. So what is OLS over here? Model is equals to OLS. So OLS is nothing but it's an ordinary least square method where you are linearly comparing for all the method. So for me, my marks are proportional to this number of subjects that I have, and I'll give my data is nothing but the new data, and I'll fit it across the particular values. I'll do ANOVA is nothing but this least square ANOVA. So what I get is this. So it will give me my degree of freedom, my sum square, mean square, F statistics, and the p-value if it's significant or not. So from there also I can get that, okay, if my analysis in between different subjects, how it is varying or not. So that it compared maths, physics, chemistry, biology, how many subjects I had there. It compared in between all of the groups, and it told me that, okay, there's no such significant difference if you compare in between the groups or not. Okay, so that is how analysis of variance plays a role within, and you can see if the populations of variances are same or unequal. We can compare them. Now, this is the thing that we saw. One way ANOVA, you first need to do an F test if it's not normal. So for doing all of this test, you first need to see if your data is normal or not. If it's normal, this test follow. If it's not normal, something called as Tukey-Kramer test would follow along with it. Okay. So then general ANOVA settings, like you take in the groups, different levels will produce different groups. You need to see if they are numerical or categorical, if it's continuous or not. And everything over here is randomized. You are no longer following that groups are within the same order that you want. It can be randomized, it can be continuously stored, and your results will come the same. Now there is something called as this mean square due to this treatment. Similarly, formula of the same. If you see, it's much more similar to the variance or the standard deviation that you compute through. So mean square difference from the particular mean divided by the degree of freedom of the same. Okay. Similarly, you have mean square error over here. Now, mean square error, sum of squares error, you need to account for these methods when you're trying to trying to do something different. You're trying to do or develop a particular technique that's different from the standard one or from the ground truth. So there you need to account for this mean square errors, your sum of square error, what's your difference, the noise, not noise, it's like what this particular Euler matrix comes to be across, what your spatial similarity index comes to be across. You'll need to account for these variables when you're trying to compare in between your techniques if you're trying to do something like that. Okay. So something for treatment, something for error, total would be nothing but this SST. So these are the types of errors that people usually do with, but if you see, everything is assigned with its own degree of freedom, because we no longer want that our sample to have a different mean if a particular sample is taken out from it. So my sample mean would remain the same there. Okay, and remember these formulas over here. Okay. So what your mean square error and particular ratio for the same stands for, what your mean square error and your sum of square error will stand for, and how your treatment and your error is different. So these are just simple formulas that you'll have to account when you're trying to solve some questions. Okay. Then we come at the last one. So that's post hoc Tukey's test. I guess we'll take this up in next one, because you see there were some of this differences and tools, if done via through some practical examples, will help you analyze them more, this analysis of variance. So I was thinking to show you first one easy tool as this graphite prism, and first I'll show you that. Next we'll go through the assignment R. Okay. So if you have any doubts, you can let me know. Well, I'm not saying that do use this tool. Well, it's just an optional alternative that I'm trying to give you here. You can always use Python. It's fairly easy. You know how to compute the population differences in there. If not, you can also use something like this. Okay. I'll stop sharing first. Connect my screen there. Right. Okay, I hope my screen is visible here. Okay, so we come upon this is another screen that I've connected. So this is a software called as GraphPad Prism. You down, oh, it's like open it. You see there are different variables that are being given to you. New tabling graph, XY, column, group, contingency, and it will also help you solve that. Okay, in what cases, how to import your data into, and how do you group them along? What kind of parts or form the data representation visualization would be done across. So if it's a simple one, you just do column, import your data, can enter this particular values. You don't need to do this particular things. It's like you are not following, so just try and enter a new data. So to just say, let's say some n number of values, we are just taking something like this. Let's not go overboard here. Okay. Followed by, let's say we also have something like this values here. So I'm randomly putting this to values. Okay. First is my A group, next is my B group. Okay. Now I want to compare these two groups. What I'll do is like I'll go into analyze. I'll first check if my groups are normal or not, if they are following normality test or not. What do you think it will follow or not? Well, next what we do, we say it that you need to follow normal Gaussian distribution, no normal distribution. Another thing that you see that your p-value is like we give it a significance level, the alpha, the type 1 error to be 0.05. So 95% significance interval. Okay. Methods it will test with would be, so these are the different tests you check your normality with. So this we probably skip in this ones because I don't know why, but there are certain tests with which you check the normality, and you also have formulations for the same. You can also do this in MATLAB and Python. So you can check with Anderson Darling, you can check with Shapiro normal, Shapiro Wills test, and the other two tests are something that this particular software came up with. Okay, you do okay to it. Now the software help you analyze that, okay, following this all test, if your distribution is normal or not. The first one had pretty homogeneous values, like everything within 10, everything followed a similar range. Second one didn't. So, well, it was obvious that our values would be something like the first is a normal distributed data, and second is not a normal distributed data. Now, to start with, let's just take that all our population data is normally distributed so that we can well understand that what the variation comes like. Okay. Okay. So let's say we reanalyze our data again. So you analyze it, normality test, log normality test. You analyze the table again, create a new table sheet, do the same things again, and okay. Now you see your data is normal. Well, this was an actual example of data fabrication. Never do this. I'm just showing you how to proceed when your data are normal. Okay. So you see that, okay, it has passed a normality test, it has passed a normality test. Now, similar to Python, it computed using the t-table. It went on, saw its algorithm might have feeded it those particular values. It might have those indexed values in here, and hence it shows that, okay, is it passing the normality test? And it's giving us normal English values to interpret with. Yes, it's saying that, yes, it has. Yes, Prajakta? Well, I guess that was by mistake. Okay.
Excel or something.
Yeah, go on, sorry.
What is used in this? This look like Excel sheet.
Sorry, what is
or
using?
something.
That means?
Means Prismate, it's graphics, other graphics, or
Ma'am, which tool you are using?
which
So
tool
this is
is used here.
GraphPad Prism. I told, right? The software is
Okay,
called as
ma'am.
GraphPad Prism. Yeah, yes. Okay, so then you compare. You saw that your data was normally distributed. So next what you do is you do t-test here. Now there's also an example of ANOVA. Can you do ANOVA here?
No, cause it's
Yes.
not greater than 3.
Yeah. So ANOVA is like more than two groups.
More
For
than 2,
two
yeah.
groups, you can, yeah, yes. For two groups, you can compare with the t-test. So we do, okay, t-test. We compared, checked it. Now what we have, so just now we saw that there were dependent samples and independent samples. Now for me, my A group and B group is entirely independent. So I'll say they are not paired. Two different groups are different. If it's been paired, then it will check both of them accordingly. Now it is unpaired. For me, my data set was normally distributed. So hence I'll do some parametric test there. And I'll assume that both of the population have the same standard deviation. That is how usually it's being done. Okay, I'll just do okay and it will show me, okay, what's the p-value of my test statistics? It is 0.025. So initially what I assumed that, okay, probably some standard deviation of this particular population is greater, or if I'm able to distinguish it, or if my variance is higher, lesser, whatever your hypothesis might be, you'll be able to check with them. So you see that, okay, your p-value significant summary comes at it's significant. Whatever hypothesis null was there, it is now you reject your null hypothesis, your alternate is true, and this was a two-tailed t-test that it computed. Now you can also make a graph within the same. You just go whichever plot like you, it's not like it's on your liking, it's based on your normality or not normality. So if your data comes out to be normal or not normal, you decide if can be a bar graph or not. If it's not, always be safe and go with the box plot. Why? Because it will give you this median line in between that will help you interpret if your population is normal or not. Then you go with Tukey. What Tukey stands here is it will help you know. So we studied the concept of this interquartile range, right? So we saw that this 25% and 75% in the first two sessions, that how your first quartile Q1, Q2 and Q3 has been split into. So here you have the flexibility and you just plot it. So it helped me plot this particular two particular variations. I said this was my group A, this was my group B. Now, if it was not normal, you would do some non-parametric test. Okay, so let's say if I changed my values here. Okay, let's say my values are something like this. Let's see what, so I'll follow the same steps. First, I'll do the normality test. Now it came that, okay, it's not normal. Now, can you say why not normal? So, well, it's not normal because you have something that is nothing but an outlier or something that does not belong to this range of data, that is this 44 value. So, hence your data came out to be
44 is
not
the
normal.
outlier.
Yeah,
Yes, ma'am.
exactly. So then you analyze the test again, you do a t-test. Now your analysis would depend that your data set is not normal. So what you do is you use a non-parametric test. And for this software, it follows a Mann-Whitney test. So there are this couple of tests. Probably professor will expand on this particular test whenever we go ahead in the lecture series. So you'll all be a cohort with it. Now let's now just to see what it saw that my p-value is 0.3875. When these data sets are not normal, it says that the values or whatever your null hypothesis was, we cannot reject it. We have to go forward with the null, and our alternative hypothesis had to be rejected. So this was another way. Apart from Python, how do you is like using some tools like this, how can you compute this particular values, and how can you see if your t-test statistics are different or not? Okay, so I'll just disconnect from this software. And so this was all about how do you do this test statistics apart from Python, and if it's easy for you or not, if whichever way you like it to be. Okay. So now since it's
Ma'am,
done,
is the tool is cloud based? Means we can import any data files.
uh yeah, yes, you can import your Excel files in there, but
Okay, ma'am.
that software it's not, it's like for me it was like we are able to use it through institute license, For another users which are using it for the first time, you could use it like it gives you a 30-day free trial, and followed by the 30-day
Okay,
free
ma'am.
trial, it will go and you won't be
Okay,
able to do it's only viewing like that. Okay.
okay, ma'am.
So with that, we are done with today's lecture and summary of what it was. Post-hoc analysis we will do when we have more a couple of examples and you will be able to understand. So probably in the post-hoc analysis, the test would be covered up here, but I went through them. It was more theory for me. That's why I thought, okay, we'll have more examples and we'll do that again. Okay, so if any of you have any doubts, you can raise them now, or else we can go towards the assignment. Any doubts, any questions? Mm, if not, let's continue with our previous year assignments. Okay. Okay, my screen is visible. The assignment questions are visible. Okay. Okay, so you guys can start firing if you know the answers here. So in the analysis of variance procedure, that's nothing but ANOVA, the term factor refers to. What is an factor there? Is it a dependent variable, an independent variable, have different levels of treatment, or a particular critical value for their statistics? So you can completely rule out the last
Independent
example, right?
variables.
Yes, so that's
Mainly
an
independent
independent
variables.
variable. Yes, so that's an independent variable. If it depends on something, the further analysis will be like, okay, if it's dependent or not. But at first, to start with, the factor always states for it independent variable. Okay. Next question. If you know the formula for it, in a problem of solving it for three treatments, 10 observations per treatment, the sum of square error comes out to be this. What can be your mean square error for this definition, population? So if you don't know the formula, I can help you here. Mean square error is sum square error divided by your degree of freedom. So you can start computing from here. So what would be your degree of freedom here? How would you do your degree of freedom? So there are two ways here to compute your degree of freedom.
Ma'am, it's n minus k, means the population uh, size minus the 3.
Okay, so do we consider my population size as 10 and minus 3? So
10
that's,
is the population size and 3 is the total treatments.
well, you read here. So it's like 10 observations per treatment.
Yes, ma'am.
So it repeated 3 times.
Mm.
So one way
Yes.
can be you do directly 10 times 3 minus your 3 treatments. So that's like 30 minus 3 gives you 27. Another way can be, if you don't know, just go with the initial way. It's like 10 minus 1 times 10 minus 1 times 10 minus 1. So 9999. Oh, sorry. What did I do? Sorry. Not this way. Another way was what?
Ma'am, the answer is 14.8.
Well, yes. Answer is 14.8. So you computed the degree of freedom like this or some other way?
No, only this way.
Okay.
That
So,
multiply by 3 minus 1 minus 3.
yeah, yes. So that's like observations were per treatment and n number of times, how many times you have it like this. There was an option 1 too. I guess it was like n minus 1 times k, something like that. I'll check upon it. Okay. Next is what was the F ratio in a completely randomized ANOVA? Well, we know that F stands for the ratio of the variances in a population, but in terms of this, how it is? Well, okay, we can rule it out like, okay, it's not always the ratio, it's not the sum of squares, it's always the error there. What would be on top? Would be a total or a ratio? If you don't know
MST
things, you can
divided
check.
by MSE. Option second.
This one? Well, no, it's like, it's always a ratio, right? We can
Ma'am, I am audible.
cross. Hi, yes, you're audible.
Ma'am, first MSTR or MSC is the right answer, ma'am.
Yeah, yes. So MSTR by MSC. So in this type of questions, you can always see that, okay, F ratio stands for the ratio of your variances, where variances are compared to the error. So now you have to see within this particular randomized area, you compare this ratios when it's randomized, but divided by the error of it. You don't always take the mean square total value of it, okay? Next thing, we have some here, I guess. Okay, so we have this procedure is applied to a data obtained from 6 samples, where each sample is having 10 observations. The degree of freedom for the critical value F is what? So you'll have your degree of freedom different for this, different for this. So first, let's just take, it's for 6 samples, right? So here your degree of freedom would be 6 minus 1, 5, right? Next it said that where each sample contains 10 observations, right? So what it would be? The sample of observations would be 10 times 6 minus, there are 6 samples, so that is like 54. So what would be the answer here? For the sum of ratios for F, what would the values would be? 5 for numerator,
Answer,
54 for
answer C is
denominator.
right. Answer 5 numerator and 54 denominator degree of freedom is the right
Yes,
answer.
exactly. Thank you. So next thing, we need to compute. So we have been given a total value, a ratio value for the residual values. We need to compute the sum of square error. So how do you compute a sum of square error? We already said that, okay, these are the two things that are sum of each other them. Now you have a total value given to us. What will you do? The error is nothing but, yes,
SST
go on.
minus SSTR.
Yeah, yes. So what would
SST
be the,
minus SSTR.
yes. So what would the answer here?
OT.
Yes. Okay. Next is the critical F value. You have your numerator, you have your denominator. So at alpha is equals to 0.01. So probably this is something that you need to compute, see at the F table and compute the value through it, or you can do using Python also. Okay, so compute the particular value for, so do the F stats for that particular value. You'll be able to compute the values there. Okay. Next is, okay, so you have two independent simple random samples taken to test the difference in between the means of two populations. The standard deviations are not known. Okay, and the sample size first is this, second is this. What can be the correct distribution for this? Can it be T or can it be Z distribution?
Ma'am, T distribution with 48 degree of freedom.
Okay, so would you like to expand it for everyone? How did you do that? Well, okay. So if there are two populations and you need to see that which particular thing you need to account for. So what do you do is like you compute the entire degree of freedom as n1 plus n2 minus. So these are two population. You always, oh, you had n1 minus 1, you had n2 minus 1. So that's like minus 2. So you do 15 plus 35. So that itself is 10, and for 50 minus 2. So that is 48. Okay. I hope this is clear for the ones who didn't get. Next thing, the sampling distribution of populations P1 bar minus P2 bar is approximated by what? So which particular distribution did we do we go if it's for a population proportion? Well, we saw that for population proportion, we never used a t-test, right? So all of these things get nulled out. Now, what's the only option there? is a normal distribution, but that's also not a correct option. If you want to elaborate more of it, how would you say that only z-test is possible? And again, if you need to compare it in between more than two groups, which particular test is possible there? We just saw it now. When we were generalizing, yeah, yes, and
Chi-square test.
yeah, yes. So the chi-square test. So if it's for this population proportion, and if that's your more higher sampling distribution, it's more general option is given over here. That's normal distribution, but it would have been more elaborate. Then you can do the z-test one. Okay, so only z-test is possible in case of two proportions. Okay. Mean marks obtained by male and female students of schools ABCD in the first unit set is given over here, and we need to compute the standard error. So you all by now must have known the formula for standard error. So the basic formula is this: sigma by root n. I won't tell you what's the formula for the entire thing. You can compute it. So that's similar, follows the same trend. So keep in mind that the population variance is given to you. You can tell the formula or you can say the answer.
Ma'am, 2.0.
Yeah, yes, 2.0. Can you say the formula for everyone?
Ma'am, it is using S by routine. Maybe S is the sample size. I'm sorry, S is the mean marks, and N is the sample size.
Here. So this has been given you to confuse you at first.
Okay.
The standard error of the two means. Yes? Who said the answer can say the formula? How do we compute the standard error in this case? So you have your sigma square 1 by n plus your sigma square 2 n1 and n2. Your first population variance is given to you. Your next population variance is not given to you. And how do you do that? Who said the answer? Your n1 sample size is given to you, but these things are not given to you. How do you compute those? Someone said the answer, right? I want all of you to think in that way. That's why. Who said the answer? Can bring up courage to say the formula also. Someone? Or else someone knows, apart from the person who said answer, another one, someone of you know how to compute it? So these are the kind of examples which are just easy to go through. You don't need much more time here to think on. These are also something like which will come in exam. Who said the answer? I guess Arunaba or Alpha S. Who said the answer? Responding. Someone trying to say something? Okay, I guess I'll leave this up to all of you to figure out. Okay, you have this 128 here, you have the sample size here of it's different.
Ma'am, can you please explain again?
Alright, so the formula to compute this, who said this thing? Okay. So this would be your population variance that's given to you. That's nothing but Oh, please don't unmute yourself again and again. Yes. So your population variance here is 128. Your sample size is given to you. Next would be your entire population variance across how many marks you have here. So this is nothing but minus 100 that, and this is like minus variance is like minus the probably, let's bring on the calculator. 28 plus 72. So, apart from 200, I guess, so if you compute for entire thing, your sample size is 64. So you have 128 by 64 plus you have 72 by 36. So why so? Because 36, 64 plus 36. So you have been given this thing, mean marks obtained by male, and of this in the first unit test having shown the standard error in between the two means are what. So this is your entire sample size. So for the males, this thing is given. So you compute it for females. So that would be like 36. Now you know this particular value is 128. Probably I am not getting how they confuse me. It's like, so you take a difference between this, so you get 72 here. So they should have mentioned what's the total sample unit here. So let's say if it's 200 here, and this can be is like total population is 100 here. So you get this two numbers here, and that would be feed in your numbers here. So 128 divided by 64 plus 72 divided by 36, and take square root of them, you get 2.2. Okay. This is for the female population. Okay. Next up, refer to the first
Ma'am, how we
question.
get the another population variance? Means one
So,
population variance is given here, and what's the another population variance?
yeah, so for this kind of questions, probably if they mention the total number of students in a class would have been good. Here they haven't mentioned, and I just directly assume that, okay, if it was 200 and subtracted it from it. So,
Okay, ma'am.
directly that way. Okay. So if you refer to the first question again, if you are interested in testing whether or not the average marks of males is significantly greater. Okay, someone's trying to join again. If the average marks of males is significantly greater than that of the females, the test statistic is what? So what do you do over here? You compare the mean difference in between both of them divided by your standard error. What's your standard error? That is sigma by root n. So you compute the t-test statistic for it. So what you do is like you have the mean for this particular sample, take the mean of next particular sample. So what this mean of this sample would be? Sample. So the sample size is given to you, population variance is given to you. How do you compute the mean x bar of the second population? Sample mean for this population. Anyone has some hints on this? If we just do P and Q, something like that, sample variance won't be directly difference of it. So sample mean would differ for. So we'll have to see the way how the sample
Ma'am,
mean will differ.
ma'am, average marks of males 44 and average marks of female 41. Right, ma'am?
How come you bring that?
What, ma'am? Sorry.
From where this number 41 came?
Because oh, sorry, ma'am. Ma'am, X2 is a 64.
Sorry?
X2
Huh?
uh, uh,
Uh-huh.
is a 64, right?
So the first sample size is 64. Second is 36. You have sample mean for males as 44. What can be for females? I don't know if I'm missing something here or not getting, but okay. Mm, Whatever that person said, if it's 41 here, you all can also check. And if you know the mean over here, then you can compute x1 bar minus x2 bar divided by the standard error. So we already know what your standard deviation, the standard error was, and then you can compute the t-test statistic for the same. So what did we compute here was the standard error for the difference. The standard error was 2 directly here. So you can input it in 2 here and you just need to compute the difference in between both of them. So this is how you do these things. I'm not still able to understand this thing. I'll let you all know if others are also not getting this thing. Okay. That's it for today's session. If you have any further doubts, you can let me know, or else we can close the session. Thanks for attending. Okay, if you have any doubts, you can let me know.
Ma'am,
Yes.
ma'am, we are getting that alpha is the significant value. This is 0.05, means the 5% of error, right?
Yes. Yes.
Okay, ma'am. And type 1 error is happening cause the 1% of error, means the significant level is 0.01.
As type 2.
This is type 2. Means when
So
the significant level is decreasing with uh, type 2 error will happen.
well, so if you don't see these things in that way, so it's like the level of significance, like whether it's 0.05 or it's 0.01, depends on you. So how your research question wants you to be, how strictly you want to
Oh,
know that, how much significant your sample size should be. So let's say in biological cases, you always won't get this, you always won't, or you always would get a value of significance. So for those cases, what people do is like they'll always go with 0.05, that's 5%. But for let's say problems such as in maths or physics, experimental problems, they don't come to this particular precision. So for them to prove some phenomena or theories that they are working with, they want a higher degree of freedom. It's like higher level of significance there. So what they do is like they take values close up to like say 0.0001, like that. So for them, the level of significance varies. So this level of significance are like played on according to your own risk.
okay,
Usually
ma'am.
people follow 0.05 for alpha and 0.02 for beta. So that are like usual general trends.
Okay, ma'am. Thank you.
Okay. Thank you. Yes, someone wants to say something?
No, ma'am.
Thank you.
Ma'am,
Yeah, yes.
without Python application, can we do it in command prompt, ma'am?
I don't know if stats you can do in command prompt. Well, I do know that, okay, basic maths you can solve there, but I'll have to see if basics, this stats, if you can do in command prompt or not, because you'll need this certain libraries there, right? Command prompt follows everything that's available in Windows, and hence we have this substitute for Python, which will help us download the different libraries from it. So we'll have to see if command prompt will have those stats or not. So that again depends on its inbuilt libraries. If it has those, it can. If it does not, or if there's a way to include all of those, then I probably am not aware of that.
Thanks for that information.
Thank you. If there are no further doubts, then we can close for today and we'll meet Tuesday. So this week, Tuesday, it was not possible because I had something. So in the next week, we'll meet on Tuesday. Okay, so thanks for joining. Thanks for attending the session. We'll cover up week 6 in the next week.
Thank you,
Thank
ma'am.
you.
Thank you.